My name is Rob Horner. I am a customer engineer in Google Cloud. I've had the privilege of working with Sling TV over the last year with some really exciting things they're doing in transforming their workloads. You heard this morning that a big focus in Google Cloud is making it easy to deploy and making sure you're not locked in. So the promise of serverless networking, or serverless computing, serverless workloads to minimize operations, and open source tools, or managed open source tools, that really allow you to run the workloads you want to and still have the power of the open source community behind that. I've had the privilege of working with them for about a year now, and watching this journey over the last probably 9 months as they take existing machine learning workloads, machine learning algorithms that had been built previously, and moving things into GCP and all of the things that they got to learn along the way. And we all love to learn stuff along the way. So Austin Bennett is a senior data engineer with Sling Media. And Salma Riazi is a data scientist, also with Sling Media. And they're going to give us a little glimpse into the journey that they've had over the last 9 months. So Austin, you can kick it off.
Let's see, is this, all right, cool. So far, so good. Cool, I think he just covered that. So I'll walk you through the agenda to start. Why is it that we're playing around with GCP at all? A bit about our data and overview of the sort of things that we're addressing, how we took things from a local laptop to virtual machines to using cloud machine learning engine. No machine learning project can work well without data being where you need it. So some thoughts on how to move data around and migrate it. A bit on preprocessing with Dataflow and Beam, and digging into how to automate some prediction using Cloud Composer or hosted Airflow in the open source sense. So for our motivation. We had used to be a analytics group, so just reporting for things around Sling TV. But the goal wound up being we needed to support machine learning workflows for a bunch of reasons. The current tools being managed database services really aren't great for machine learning workflows. So we needed to change our tooling and infrastructure. One way I think of a trade-off that is needed in a lot of places is a data warehouse versus a data lake. So data warehouse being really just a SQL kind of engine, could be your MySQL or whatever store, or some MPP system, is super familiar to many people, and updates are really straightforward. The ability to, in a data lake, to otherwise work with machine learning flows, just read the data off of some form of, say, blob storage, super nice for Spark ML and things like that. So kind of where to use which system so you're not trying to unload your data out of a database itself. Also kind of an origin, our group was nice and sent me to the KDD conference in 2017 to keep track of research in the area. There, you guys may have come across the TFX paper on things around TensorFlow and a really nice way to productionize machine learning. So was familiar with that and eager to follow the developments, and have been attentive to that. Open source, super cool. I don't like managed services where what's going on under the hood isn't apparent, as well as then I can really dig into the code and understand what's going on. So here's a whole lot of things that we either had been using or made sense to jump into, and then really a quick shout out to these other things where trying to get through the whole infrastructure and pipeline to some more even opsy sort of things. And then really what kicked off this process was the Cloud Next last year. So where you guys are now, as well as we as a group came and saw all the great things other companies were doing. So it made sense to really dig in and figure these things out. And Salma's going to share a bit on our data and background.
Hi, everyone. Thanks for joining our session. I'm going to start talking about the data and background and the many iterations we have to take in order to get to our end-to-end machine learning pipeline that we have today. So how many of you know what Sling TV is? Well, that's so many. For those of you who don't know, Sling TV is an online TV platform where users can sign on and watch online live TV and on-demand content. And like so many other subscription services, we're concerned with customer churn. We want to identify the customers before they churn so we can do something about it. For this binary classification problem, we can look at so many different features. For example, what users watched, what channel they watch, how long they watch it for, what day of the week, and the time slot. This is just an example. We can look at millions of attributes. So for this churn prediction problem, let's assume that we look at 6 days of activity and want to predict churn at day 30. For this one user, the user subscribes on the first day and watches ESPN for 1,500 seconds, and it's a Monday night. They come back again on the second day, they watch Food Network, and it's Tuesday, 6 to 8 p.m. They don't watch anything on day 3 and 4, and they come back again and watch some travel channel on a Friday morning. For many non-deep learning models, this data needs to be aggregated per user. So for that one user, you will have total number of seconds watched, channel most watched, total number of sessions, was it mostly a weekday or weekend, and most common time slot. However, this kind of model will disregard the daily pattern of user activity. There are these studies online, the papers that use convolutional neural networks for churn prediction, and they use daily patterns, daily activities of users. The model architecture for this kind of model has multiple convolutional layers, followed by max pooling, and then it gets to a fully connected layer, and then it will get to a final softmax or sigmoid output for the final classification. I don't see the slide. Sorry.
The screen's flickered and out. Okay.
In order to use this kind of model, we need to clarify between days of activity and inactivity. So for the days that the user has been inactive, we need to insert zeros. For example, for the days 3, 4, and 6, we insert zeros for the numerical values and encode the categoricals. Then before feeding this data into the model, the data needs to be encoded and scaled. For numericals, it needs to be scaled between 0 and 1, and for categoricals, it needs to be encoded. So after trying that, we were able to improve our model metric by 15% compared to our baseline non-deep learning models. For that one sample, if you look at one user for 6 days of activity with 5 features, it's very simple to pre-process and train the model. However, with many, if you want to look at a more granular time standard, for example, minutes or hours, and for millions of users with thousands of features, this problem gets very challenging really quick. So now I'm going to talk about how I did the pre-processing and each iteration. First, I started small with data warehouse. I moved the data to a virtual machine, pre-processed and saved the data on the virtual machine using pandas and NumPy. I'm going to get into the details in the future slides. I trained the model. It was a Keras model on the virtual machine, did predictions. On the virtual machine, the only thing is that I needed to pre-process the predictions the same way that I pre-processed the training data. And then I saved the predictions to the original database. So we realized quickly that that system was not, it was not good for production. It's not very scalable. And we wanted to move towards a serverless scalable system. So we started changing our tools and moving to GCP. First, I started with the original database, moved it to Google Storage, and did the pre-processing on Data Lab using the same functions and same tools. I saved the pre-processed data to Google Storage, did the training with Keras on CMLE, cloud machine learning services, and did the predictions on virtual machine. I did this because last year, Keras was not compatible with the model API, but I think today things are different. After that, I did the predictions on the virtual machine and saved the predictions to the original database. Again, I needed to do the pre-processing on the prediction data. This is detail about the code I used for the first 2 iterations. First, I read the unloaded CSV file into a pandas data frame. Then I scaled and encoded the data, and then I set it to a NumPy array while inserting zeros to the for the reason I showed earlier. And then I saved the NumPy and pickle files. The encoding was I did the encoding using label encoder and standard scaler by scikit-learn. I saved it to pickle files, which I needed to keep track of throughout the modeling process. The problems are scale, the extra packages, the pickle files, and prediction pre-processing. This is how the model architecture looks like. It will first, if you look at the first 4 lines, I am reading the whole NumPy array at once, and then I'm loading the pickle files. The problem with loading everything at once is that if you look at the bottom part, I get an out-of-memory error in cloud machine learning. And then after that, it's just a normal Keras model. Before solving the out-of-memory error, while the data was small, I experimented with hyperparameter tuning, which is a really cool tool. You can set your parameters and experiment with it. So here, this is a very exaggerated hyperparameter tuning example. You never want to experiment with this many. But here I am tuning, I'm trying to experiment with number of filters in the convolutional layers, batch size, optimizer, and dropout size. On the right, you will see the YAML file that is submitted along with the job. And in there, you will set the ranges that you want to try. For example, if you look at the optimizer, there's Adam, SGD, Adam Max, and others. On TensorBoard, you can follow all these trials that are being run. And based on your model metric, you can pick your favorite one. So here on the lower left pane, I picked number 18. And on the Google Cloud Platform, you can go and find what number 18 hyperparameters were. So here, the first conv layer, the number of filters were 112, and the optimizer was AdamX. While in TensorBoard, you can also check the model graph and see if everything looks expected and if anything stands up for troubleshooting. So now back to the out-of-memory error. I still needed to solve that part. So this time I started with the original database. I moved the data to Google Storage, did the pre-processing on Data Lab, and saved the NumPy array again. But this time I converted the NumPy array to a TF record file. So I could use it I could use TF data in TensorFlow to read the data in batches. And then I did the predictions on the model API in cloud machine learning and saved the predictions to BigQuery. Again, I needed to do pre-processing on predictions. So here's how I converted the NumPy to TF record file. I used an image example, which saves all my features to a feature called X, which is inconvenient because later it will be hard to get to each feature by name. But this solved the out-of-memory error and the scale issue. So this is the model input data and architecture. First, you need a parsing function to parse your input, the TF record file. Here, there's X and Y. X is all the features combined in one. The input function, it will read the data in batches, and you can set it to shuffle your training data. So just a reminder, this is where iteration 3 is. Everything is almost in Google Cloud Platform except for the beginning part, which is the original database. And now Austin will take us through how he moved that to BigQuery.
Thank you, Salma. OK, cool. So I meant to switch the order of these slides. OK, so BigQuery is great. I mean, I talked about a trade-off before of between a data lake and a MPP database. Realistically, BigQuery gives you the best of both worlds. Like curating data and needing to think about the files on a storage system is a pain, and I don't want to do it, and I'm glad there's a managed service for it. I can update data and not think about things. It's as performant as anything else I've seen. Haven't needed to do a ton with it yet, but the ability to share data across different organizations, across projects is super straightforward. And I didn't pay attention enough earlier today as to whether or not the BigQuery Read API was talked about, but it's super cool, gives us direct access to the underlying storage, which, for then letting Dataflow, Beam jobs, or Spark, et cetera, access that data directly. A great way to try stuff out also, which I wish would have existed when I first got started, is there's a transfer service that input a few parameters in the UI, which I prefer to not use UIs, but this will get you moving really quick. In our case, we moved a few terabytes over and saw performance was great. Given that I just gave you great sales pitch on how great it is, I also everything isn't all roses all the time, right? So ran out of resources even on BigQuery in one specific instance, although, talking with the BigQuery team, eventually we were able to do this sort of query, which we were able to do elsewhere. They fixed things more or less, and then this became not an issue. So ML can't be successful without ingesting and moving data around. So want to talk about a few ways batch ingest from various places, third-party APIs that we may hit, and stream APIs, and using some various open source or at least managed tools. Also, containerization is pretty cool. We have, a lot of our stuff has been orchestrated from a central virtual machine, which, although has worked very well, also has its problems for scheduling resource conflicts and, packages and versions. Those sorts of things go away when we adopt these sorts of containerization practices, which we've been working towards. Many of our batch ingests are patterns like this. And also, I guess the point I'm going to try to get across in this talk too is, multi-cloud is totally doable. It's use the great tools where they exist or within the confines of your organization. If people say you need to use something, don't, it's not all or nothing. So many of our workflows are data gets dropped into S3, for instance. This is a very simplified workflow of one, say, Spark job that transforms stuff back into S3. To do things with it, for instance, just take that output and copy it over using the transfer service or GSUtil or whatnot, and then it's in cloud storage. Another way that we've played with is on data ingest in the first place into S3, copy it over to cloud storage, write that Beam or Dataflow job, get it over to cloud storage. Especially once it's there, and because we're talking about batch, it's straightforward to get it into BigQuery. Also Dataflow Beam. Okay, yeah, that arrow's missing. But Dataflow Beam can go straight into BigQuery, and then I put Poof because I think I haven't tried it yet, but I think that there's zero problem having Dataflow and Beam read right from S3, and right there, the things exist to do it, but I haven't tried it yet. But that seems like a great way to simplify my architecture. Another bit on batch ingest, we have a bunch of third-party data providers that we get data from. So hit the API. In the first iteration, GKE and a container was managing everything. So it would go to BigQuery, get, say, the last timestamp of things, go back to the API, get the data it needs, write to storage, and then we'd use a Dataflow and Beam job to write things to, say, BigQuery and Google Storage. Things got a little more simplified when adding Airflow to the mix, which then let the orchestration be in the Composer Airflow layer and smaller containers and discrete services. And then we were able to reduce like query costs from keeping the metadata itself in Firestore rather than in BigQuery and needing to, essentially using Firestore as a metadata store of the last timestamp. So just a quick key value lookup. Streaming data ingest. We have processes that look like this. Nginx and Logstash on-premise endpoints, stream to Kafka, go to Logstash. That winds up getting batched and written to S3 and loaded into Redshift. To support our other fantastic groups and colleagues we work with, we then wound up adopting more of the data lake model, unloading things out of Redshift using, say, Spark, and writing that back into S3 for columnar bits. Since we absolutely have to support S3, Dataflow and Beam, though, can read write from Kafka and are able to write to these other bits. For streaming data, we're still toying with whether we're going to get enough value out of Bigtable itself to let BigQuery read from Bigtable, write to both, or if BigQuery is going to be itself. And although Dataflow and Beam can talk to our Kafka clusters directly, we went ahead and just jumped all the way to having Nginx and Logstash forward write to PubSub. Because with the eventual goal being, let's get our on-premise infrastructure into the cloud, and it looks like we're leaning towards using cloud endpoints and cloud functions, although we're first proving out the rest of the pipeline that's here. Big fan of things Beam, and giving a shout out to this session on Thursday of my colleagues there, 11:40 to 12:30 stream analytics stuff. All right, and then Salma's going to share more on our modeling.
Thanks. So now that we have data in BigQuery, thank you, Austin, for putting in BigQuery. Everything is in BigQuery now. So now I start from BigQuery. But again, as Austin mentioned earlier, we were at Next last year, and we learned about all these new tools like Dataflow, tf.transform, that are great for preprocessing big scale data. So I wanted to give those a try, and I found these courses on Coursera that are really helpful. And Data Lab is a great tool to follow the courses on Coursera and learn tf.transform. So this time I started from BigQuery, then did the preprocessing on Data Lab, but with preprocessing, I mean submitting a job to Dataflow. And then I saved the preprocessed data on Google Storage, trained the same model on CMLE, predicted on CMLE, and wrote it to BigQuery. But this time, no preprocess for predictions. So that's great. Here's a learning example of tf.transform on Data Lab. In case you guys are interested, you can follow it and troubleshoot your code. It's interactive, and it's easy to follow examples, serverless and customizable. So here's our final iteration, which is much shorter than the beginning and scalable and serverless. We start from BigQuery, do the preprocessing on Dataflow, save the TF record files on cloud storage, do the training and predictions on CMLE, and write it to BigQuery. Here, we solved all these problems of scale, extra packages, and no more pickle files. There is no preprocessing for predictions because tf.transform writes the graph, and you can point your model to the graph of the output of tf.transform, and it will automatically preprocess it for you. Here's an example of a Beam pipeline that I used. First, I read the data from BigQuery. No more unloading data from a database. It just reads it straight from there. Second step is grouping by user, which is just reordering the elements. Then I insert zeros and reshape. I'm going to get into the details in the upcoming slides. And then I scale and encode using the tf.transform functions. And then finally, I write it to a tf record file. These are the first 3 steps. The first function is just a query. Just select the query. The second one is data validation. Here, I'm checking to see if day is greater and equal to 0, but it could be anything. The third step is collect users, which is it reorders the input elements, so it can group by later. The fourth step is the write format NumPy operation function, which is just a normal NumPy function. And the fifth step is where the encoding and scaling happens. So after the fifth step, the tf.transform graph gets written to your bucket, where you can point your model to. Here's a Dataflow example. I'm going to show you a demo later, but just in case, here's an example. You can follow each step and see where you are. You can see your job description and summary, and on the right middle pane, you can see the auto-scaling. So here, I needed 70 workers for 10 minutes. It auto-scaled to 70 and then back down. And my job was done in 15 minutes. So now I'm going to move to the demo. All right. So there's these 2 files that are very similar to what I showed you. I'm going to run it from the terminal and hope that it will work. So here's the GCP platform, the homepage. Here you can find the compute engine, the ML engine, like all these tools that I just talked about, BigQuery, but I'm interested in Dataflow. And one of them has kicked off. The graph is still being analyzed, so we have to wait a little bit. OK, so here you can follow what's happening. The first step is the BQ import, and it didn't run. So in order to check why, you can always click on the step and click on the logs. And it will give you the error, which here it says BigQuery execution failed because unrecognized name. I just put an unrecognized name there so you can see the error. All right, this is the second one, which is exactly like the one I showed you before. You can see the the steps that's running. I'm running it for my training data and also the validation data. And they all get saved. Here's where the transform function gets saved. And this is where the transform happens. The auto-scaling is kicking off. Here you can see the job information and the resource metrics and the pipeline options. You can always submit a setup file with it to specify what you want. Here's the auto-scaling. The current workers are 0, but it wants to be 70. If we wait a little bit, the current workers will go up to 70 and then back down, and the job will be done. This is the same job that I showed you the picture before. So we don't have to wait 15 minutes. So I'm going to go back to the slides now. All right, so in the model, the only thing that you need to change is the serving input function, where you point it to the tf.transform graph output. This is how it happens, and then the lower is the predictions output, where there's viewer ID, probabilities, and prediction classes. So now that we have all the pieces of the puzzle together, it would be great if we could have this automated daily. So we could have daily predictions every day. And here's Austin, who will tell us how he did that.
All right, so cool. Things should be automated and whatnot. We're doing batch predictions. One of the more straightforward ways of doing it is unload from BigQuery to get those records in new line JSON format. In this case, we used Beam Dataflow, write those to Google Cloud Storage. A second step being hit the ML Engine predict service, read those files from Cloud Storage, write them back to Cloud Storage, and then just for what we've been doing, those batch results are just going into BigQuery so we can do things with them. So it's a 3-step process. To highlight what this is, we have our Beam job, which is called extract.py. The documentation is super straightforward on how to use Beam Dataflow to do some things. Composer, Airflow, less so for these operators. I'm really hoping they wind up getting accepted for, I forget if it's summer or season of docs, where then there should be some resources helping even the open source projects get some documentation going. But you can take more or less the Python command line and translate that into what's needed for Airflow. This is for the Dataflow operator. Equivalently, hey, we see a whole lot of variables we're using, and using the gcloud ML Engine job submit. Again, documentation really great. And here with the ML Engine batch prediction operator, you can see I tried to make this pretty straightforward where it's pretty much plug and play here. And the same goes for the BQ command line tool and the load command. A little bit more to it, but also, again, pretty straightforward. So that's how we weave these things together. Yes, they can be cron jobs for those sort of command line tools that we saw, but Airflow Composer gives us a lot more visibility into stuff, and also, hey, let's learn these because those lessons get applied all over the place like we saw earlier for moving batch data around. Okay, so far, summary. We've seen how we slowly built onto our eventual solution. The real goal was how can we have in our tool set the best scalable solution that we can work on, even with, say, our 12 gigabyte data sets when we need to work with our mini terabyte data sets and anything in between. But hopefully, as you've seen, you don't have to not show any progress for a long time while you figure things out. You can work towards those solutions. Using TensorFlow stuff, we've seen better predictions, trying to get that across. And yeah, you can use open source tools. And also, we're a very small group that we've been working with. So leveraging serverless and managed services are amazing. So we don't have to. Quick announcement, also, I'm helping organize the Beam Summit in Europe. If you're into Beam Dataflow for even running things like TensorFlow Transform, check this out in mid-June. Also, there will be a Beam Summit track for 2 days in September in Vegas at ApacheCon, another place to check stuff out. And then wanting to say thanks to a bunch of people. So especially our Sling and Dish colleagues for encouraging and supporting this path, either directly or by supporting the needs of the group, so we had the time and ability and attention to devote to these sorts of things. To the GCP team that's helped us along this journey. Certainly thanks to the open source tools and everybody, either paid or volunteer in these open source communities, and you guys for your attention.